Today we will study the Osterwald's dilution law. Before studying this Osterwald's dilution law, we have to know what are electrolytes. Electrolytes are those substances whose melt or aqueous solution conduct electricity. Electrolytes dissociate when they dissociate into ions, and the conductance of the electrolytes is known as ionic conductance. Now we know strong electrolytes. You have read what are strong electrolytes. Strong electrolytes are those electrolytes which dissociate completely. That means in case of strong electrolytes, conductance will be higher as they dissociate completely, and in case of strong electrolytes, degree of dissociation degree of dissociation that means fraction of the substance is dissociated, we denote it by alpha, is high. In case of strong electrolytes, degree of dissociation is high, and that is always in strong it is equal to 1. And weak electrolytes are those electrolytes which dissociate partially. For example, if we take the strong electrolytes examples, these are acids. For example, if we take H2SO4, if we take base sodium hydroxide, if we take HCl, if we take aqueous solution of NaCl or melt, these are strong electrolytes. And weak electrolytes, if we study the example, then it is, if we take example of acetic acid, ammonium hydroxide, these are weak electrolytes. Now if we take a weak electrolytes, weak electrolyte dissociates partially. It dissociates partially, and degree of dissociation, in case of weak electrolyte is low, less than 1. Now let us consider a weak electrolyte. It is acetic acid, CH3COH. I have written the formula. Acetic acid, if we take it in water, it dissociates partially. It will give CH3CO acetate ions, and there will be hydronium ion, H3O positive acetate ions, and there will be H3O hydronium ion, acetate ion, and hydronium, H3O positive ion. Since there will be equilibrium attained between the dissociated and undissociated ions, therefore we can apply the law of chemical equilibrium to this. So applying law of chemical equilibrium, you have read K will be equal to, I will write, it will be CH3COO, that is molar concentration, or we say it active mass of acetate ions, into H3O positive hydronium ions. This is which the I have written the acetate ion in the square brackets. Square brackets indicate the molar concentration, which we call the active mass. So this is the molar concentration of acetate ion and H3O divided by molar concentration of acetic acid. I have written it again in square brackets, and concentration of water. Now if since the solution is very dilute, so the concentration of water remains constant. So concentration of acid, this water remains constant in the dilute solution. So I will say that if we take water as a constant, and if we multiply this constant and this equilibrium constant, I will write a new constant that will be Ka, dissociation constant of acid. I have multiplied, since this H2O, it remains constant, its concentration remains constant, so I will multiply that. I will multiply K into H2O concentration. I will give it a new constant that it is Ka. So I have written this Ka here. Ka is equal to, that is CH3, concentration of molar concentration of acetate ions, into H3O hydronium ion concentration, divided by concentration of CH3COOH acetic acid. Now this is the dissociation constant of Ka is equal to dissociation constant of acid. Now if I consider C is the concentration of acid, if C is the concentration of acid in moles per liter, and alpha is the degree of dissociation, alpha is the degree of dissociation, then at equilibrium the concentration of acetate ions and water will be, hydronium ions will be, concentration of acetate ions and hydronium ions will be C alpha and C alpha. I will write it in the equation. For example, it is CH3COOH plus H3. It is the reaction. We have some dissociation reaction which I have first written. H2O gives CH3COO negative plus H3O. So now I have read concentration of initial at C is the concentration of acid. I will write the concentration of acid is C. So at that time when the reaction was not started, the reaction initial stage, concentration of acetate ions was 0, that is, and that of hydrogen ion was 0. So if we start with 1 mole of electrolyte, I will start with 1 mole of electrolyte, and let alpha is the degree of dissociation. Then I will write after some time at equilibrium. At equilibrium, when equilibrium is attained in this reaction, we will get concentration of this acetic acid will be C into, I have started with 1 mole of electrolyte, C into 1 minus alpha, because alpha is the degree of dissociation. Here the dissociation takes place, so it will be the concentration of acetate ions will be C alpha and concentration of hydronium ions will be C alpha. Therefore I will apply this value into this equation. Here I will apply this value C alpha and C alpha into this equation here. So Ka is equal to C alpha square, C alpha into C alpha divided by C into 1 minus alpha. That is Ka is equal to C square alpha square divided by C into 1 minus alpha. C into 1 minus alpha. This equation becomes dissociation constant of acid Ka is equal to C square, here to C square alpha into C to 1 minus alpha, C and C it will be C into alpha square divided by 1 minus alpha. Here the equation is here, C and C will cancel, it will remain C alpha square into 1 minus alpha. So since in case of weak electrolytes, alpha is very small, that is degree of dissociation is very small and can be neglected. For example, this alpha can be neglected, so Ka is equal to C alpha square, Ka is equal to C alpha square, or alpha square is equal to Ka divided by C, or alpha is equal to under root of Ka divided by C. Now the degree of dissociation, that means degree of dissociation can be obtained, it can be calculated mathematically if concentration is known. So if Ka, अगर आपका K भी मालूम है, सो कंसंट्रेशन क्या अल्फा कैन बी, इफ K आपका मालूम है और कंसंट्रेशन पता है आपकी, so you can calculate the degree of dissociation of weak electrolytes. Now I will consider if V is the volume containing 1 mole of the electrolyte, then C becomes is equal to 1 by V. C is equal to 1 by V, containing 1, C is the volume containing 1 mole of electrolyte. Therefore alpha is equal to under root of Ka into V. So alpha is equal to under root of Ka into V. So here we can, from these two equations, we can define the Ostwald's dilution law. For example, for a weak electrolyte, the degree of dissociation or ionization is inversely proportional to the concentration, is inversely proportional to the degree of dissociation for a weak electrolyte is inversely proportional to the concentration, square root of the concentration. Square root is inversely proportional square root of the concentration, that is molar concentration, or it is directly proportional to the square root of volume containing 1 mole of electrolyte. From this equation I have written first, this is the equation first, the degree of ionization or degree of dissociation of a weak electrolyte is inversely proportional to square root of the concentration, or the degree of dissociation or ionization is proportional directly to the volume, square root of the volume containing 1 mole of electrolyte. This is the Ostwald's dilution law.